the derivative of any function, because we have this d2 psi over dx square plus k square psi is equal to 0. To understand the matrix formulation, we first define what is the derivative of any function, suppose f dash x. So for limit s tends to 0, h is some kind of a step function where any function is just take some value like x plus h. For an example, I am having some function f of x, we are having some function like this, and here different points corresponds to x. Okay, now this is x naught, suppose this is x naught plus h, some infinitesimal value increment in x naught, and we are having some different functions. So let's take this original function, subtract it, and with the step, h is called step function. So for example, I can write this whole definition in terms of a very initial manner. What I can write here, f dash I, suppose upon example f dash I is equal to, I can easily write that some function which is taking a value just from its increment place and subtract from its original place divided by h. Okay, now I can also say that, suppose for example I am writing here I goes to I minus 1, and my definition will be the same definition will goes like I minus 1 by h. So the idea of defining the derivative of any function is you take the value at certain point, you increase or decrease from that value and just divide by the step, you will get the derivative. And now since my derivative is a second order, Schrodinger equation is kind of a second order derivative equation, so I have to do the second order derivative, and my derivative operators are linear. That's why what I can do is I can write fi plus 1 minus fi to the power dash 1. So this derivative once goes for fi plus 1 and again once goes for fi. So see here, I'm going to do it for I plus 1, increment one more place I plus 2 and subtract it from its original place over h. Similarly goes from I plus 1 by I over h. I hope it's clear to you what is how the definition work. Take LCM and do this guy here. So I am going to do here like here fi plus 1 minus and minus become plus, therefore fi. Again I am going to do this thing, I goes for I minus 1, and I am having the definition for fi double derivative is nothing but fi plus 1 minus 2 fi plus fi minus 1. Okay, so here we can say how we have defined our second derivative, and this derivative is appeared in terms of an initial equation or this indices. Okay, why I'm calling this initial equation, because this is kind of indices. Now I am not taking some kind of a h and something, I am writing it kind of a I like function in different places. It will take some different values. Let's apply the same idea for the Schrodinger equation and let's see what will I get. So the idea goes like here, like psi I plus 1, I think 2 psi I plus psi I and minus 1 over h square plus k square is my eigenvalue, and then psi I, because it's the original function, psi I is equal to 0. So if I am doing right here, psi I minus 1 multiply with h square, and let's do it psi I and psi I. Let's take it common. We're having outside the negative sign and h square k square, simple algebra. You can do this thing. If you will try I plus 1 is equal to 0, then what will happen? Now here I am having the two boundary condition correspond to psi is equal to psi 0, which is my psi of x is equal to 0, it gives me 0, and psi at some kind of a last value. It means that because I am having the box at initial point x is equal to 0 and the end point is L, so end point correspond to psi n, which is equal to psi of x is equal to L, has to be fulfilled. Okay, these boundary conditions are so much important. So therefore, for example, for I is equal to 1, I am having psi 0 minus 2 minus h square k square psi 1 plus psi 2 is equal to 0. Now see, psi 0 is my 0, so this is equal to 0. For I is equal to 2, I am having psi 1 minus 2 minus h square k square. Okay, psi 2 plus psi 3 is equal to 0. For I is equal to 3, I am having psi 2 minus 2 minus h square k square psi 3 plus psi 4 is equal to 0. And for I is equal to 4, psi 3 minus 2 minus h square k square psi 4 plus psi 5. Well, why I am taking this I1, I2, I3, only I4? So the h is defined as L minus 0 by this I. How is your step function corresponds to this length 0 to L? Means where I want to divide this. The length I am dividing in 4 parts, like 1, 2, 3, 4. I can divide in n parts also. N goes to for 10 parts. Suppose L by 10 or L by 12. So the ith will be these equations will be kind of 10 or 20 or 30 or 50. Now the smaller will be h, the better we are having the value of this eigenvalue and eigenfunction will be so much better. If I am choosing this I1, I2, I3, I4 for just for the showing purpose that how this can be written actually in the matrix format. Okay, it's nothing else. So you need a computer to solve this kind of equations, because when you will doing this kind of so many equations like I is equal to 100, so your functions will be so much smooth function, and I is equal to 100 you have to solve in computer. You have to write a C code or C++ or any Fortran code you can write and just do it, and you will have this eigenvalue and all these equations. You have to learn it how to do it. But let me show you this thing how you can write in a matrix format. Well, one interesting thing, for I is equal to 1, 2, 3, you are having psi 1, psi 2, psi 3, psi 4. In a particle in a box, what we are having, psi was psi of n pi by L into x. And I have told you this n is 1, 2, 3, 4, 5. And this n 1, 2, 3, 4, 5 gives you the different states. And this will give you psi 1, psi 2, psi 3. So this thing is give you nothing but the another states like psi 1, psi 2, psi 3, psi 4 and psi 1. Now here psi 5 is corresponds to L is equal to 1, because I am considering here L is equal to, for example, L is equal to 1, because my computer doesn't know what's my L, so I have to give some kind of a value, and we can do any value and we can find the energy. So psi 5, again my wave function has to be Vanish as boundary, so psi 5 is again going to 0. So psi 0 is my 0, psi 5 is my 0. Okay, let's write it in a matrix form. So how can I write this matrix form? So you can see here, like I am having psi 1. Now for first equation I am having psi 1, psi 2. Make it multiply with minus 1, so that I want to make this 2 minus h square k square, the coefficient has to be plus. For a simple thing, h square k square. Okay, for psi 1 it's my plus, psi 2 is will become negative, and there is no psi 3, psi 4, so it will become 0, 0. And this suggests me here it will be column matrix psi 1, psi 2, psi 3, psi 4 must have to be equal to 0. In second equation, again multiply with minus sign, and here you can see that there is my psi 1 multiply with minus sign, coefficient will be negative of 1. It will be again 2 minus h square k square. Psi 3 is there, therefore minus 1, again 0. Similarly, for I is equal to 2, again multiply with minus 1. We see here that for I is equal to 3, my psi 1 is 0. I don't have any component of psi 1. Psi 2 becomes minus 1. Psi 3 becomes this again 2 minus h minus k square, and psi 4 I am having, this is my minus 1. Okay, for I4 corresponds to, I don't have this psi 1, I don't have this psi 2, I am having psi 3, again multiply with negative of 1, it will become minus of 1 and 2 minus h square k square. Okay, what did Dirac do? Dirac told that for ket vectors, this is my ket. Ket is corresponds to column vector, so column matrix, so this is psi goes for this one. So you see psi is my column matrix, and column matrix is represented like this one. And now psi is, I have already told you, now psi is my nothing but, I can write Cn of psi n, linear independent. I can make it expand in a linear component of psi 1, c1, c2, c3, c4, psi 1, psi 2, psi 3, psi 4. Okay, this is the matrix which having k square my eigenvalue. K square corresponds to energy and K square my eigenvalue. So this equation can be think of as like A of psi is equal to lambda of psi. Lambda is my eigenvalue, or lambda is multiplying with identity matrix. Identity matrix is having diagonal element simply just 1 1 1. So A minus lambda I is equal to 0. So lambda is working here just K. Okay. So A is matrix. Now here I am having S psi is equal to E of psi. So H is corresponds to this one and E corresponds to K square. So H is now my matrix of M cross N. Means it is a square matrix, and I can write this H. H contains like d2 by dx square plus v of x, and d2 by dx square is my derivative operator, and we have written the derivative operator in a matrix form. So this is how any derivative equation, any differential equation, or any operator in quantum mechanics can be represented in a matrix form. That's why I have called that in quantum mechanics we have two formalism. One is the calculus with the wave form, and another is a matrix form, where we are doing this kind of a algebra. This is something similarly a kind of a algebra, okay, the matrix algebra. So we write everything in a form of in a matrix form, and we solve this matrix, we solve this eigenvalue problem, and from there what we gonna so this is the equation. The form of this equation is this one. Now take the determinant of this matrix and make it goes to 0. Okay, and you will get the some value of lambda 1, lambda 2, lambda 3, and lambda 4. Lambda 4, this means here we will get 4 eigenvalues. Okay, so these 4 eigenvalues corresponds to psi 1, psi 2, psi 3, and psi 4. Okay, and now this 4 eigenvalues corresponds to H. Now H is first of all 1 by 4, 2 by 4, 3 by 4, and 4 by 4. So if you plug in this 1 by 4, you will get one value of K. Again 2 by 4, you will get another value of K. So again 3 by 4. So this K will give you this eigenvalue, and corresponds to this eigenvalue you will get psi 1, psi 2, psi 3, and psi 4. And you will check that this psi 1, psi 2, psi 3, psi 4 will form as an orthogonal, because I have already told you all these wave vectors, they are orthogonal to each other, and they are orthogonal to they are orthonormal to itself. Means psi 1 will be always showing this one. One interesting thing I am going to tell you here is that you see these psi 1, psi 2, psi 3 is corresponds to I is equal to some value. Okay, now I have considered I is equal to 4, 1 to 4. Now I can also consider I, for example 100, or for example 1000, or for example 1 lakh. I have a computer, I just write a code, and I take the loop, and it will just do my job. Okay, so I don't have any problem. It means that we are having the infinite dimensional basis. The psi 1, psi 2, psi 3, psi 4 gives you the eigen basis or eigenvector. So I can have this, for example, for this problem I have an infinite dimensional basis. So this problem has an infinite dimensional basis. As I have already told you, psi gives my n pi by L x. N can be 0 to infinity, minus infinity to infinity, or 0 to infinity, 1 to infinity. Okay, so the interesting thing arises here that this is corresponds to Hilbert space. Okay, and this whole thing corresponds to Hilbert space. So the definition of Hilbert space is that it has to be infinite dimensional. Now this infinite dimensional gives you a Hilbert space. The Hilbert space of infinite dimensional gives you so many things. It also provides you the basic postulates of quantum mechanics, that psi has to be finite, psi has to be orthogonal, all the states will be orthogonal, psi has to be square integrable, psi has to be normalized. Okay, and psi and first derivative has to be continuous, and it must satisfy the boundary condition. So it is the Hilbert, a scientist before the evolution of quantum mechanics. He has given this kind of algebra, and when Schrodinger saw that, he saw that okay fine, this is the similar thing which we are doing in quantum mechanics. So quantum mechanics is a Hilbert dimensional. A Hilbert dimensional is this is called Hilbert space. Okay, the wave function is a part of this Hilbert space, written as this one, sorry, Hilbert, and this is Hilbert is infinite dimensional. This is the property of Hilbert space, which gives you psi can be expanded in terms of this linear thing. Superposition principle comes from this Hilbert space, that psi can be expand or in terms of a linear coefficients. One more thing Hilbert gives you, that psi star, the definition of inner product, because you don't have, while they were doing this kind of a quantum mechanics, they didn't know how we can find the expectation value. So psi star was defined because of this Hilbert space. This is called the dual of Hilbert. Okay, psi star is dual of Hilbert, and psi is a real quantity. Psi star you can never measure in kind of a laboratory, so it's a kind of mathematical object, and also psi is also a mathematical object, but psi star is a dual of psi. Okay, so psi star, then psi star and psi star gives you the inner product, and you will understand what are the probabilities or what are the everything, every real measurement is because of this inner product definition. Okay, so because of this thing we are having this kind of cool definitions, and we see Schrodinger developed this quantum mechanics in a form of calculus way, and there was a Gell-Mann who developed this matrix formulation. And this matrix formulation is so much powerful, because when you want to solve this, suppose I want to find the wave function for water, or I want to analyze the how quantum mechanics of water can be analyzed. So to find the quantum mechanics, you have to write the Schrodinger equation for 2 hydrogen and 1 oxygen. So the Schrodinger equation becomes so much complex that you cannot actually write it down. You cannot solve it analytically. So you need to understand how the quantum, how can we solve a quantum mechanical problem in computers. So this is the language of computer, where it will take these matrices and it will give you the eigenvalues and eigenvectors corresponds to this, and you will see all the spectrum and so on and so forth using this computer. So that's why this matrix method is so much important to understand. And there are so many ways to there are so many ways to do quantum mechanics numerically. This is called the numerical method, and the method which I am using for this kind of thing is called polynomial expansion or polynomial method to find out the wave function of quantum mechanics. So this is one of the most interesting thing, and you never realize, because in classroom the teacher will tell you that there are two kind of formalism, and in so many books you will say that, oh, h is given like h is corresponds to h is written as mn. It's kind of a matrix thing, but you never realize how this matrix structure actually come, how the computer actually, how we can solve something in computers. So this is the way people think how to solve this complex problem in computers using this matrix identity. They find the determinant, and then they do the method, they have the method to get these eigenvalues, and corresponds eigenvalue, they construct these eigenvectors, and this is how numerically quantum mechanics has been done. And this is the structure which enables you to understand what is the Hilbert space and why the Hilbert space is infinite dimension, because these eigenvectors can be psi 1 to psi infinity, and this the property of Hilbert space enables you to write psi in a linear combination of all these eigenvectors. Okay, and this has also developed you, this has helped you to postulate why how the structure of wave function should be, that it has to be square integrable, normalized, and then it has to actually satisfy this boundary condition, and all the states has to be orthogonal, square integrable, and so forth and so on. So you see, the conclusion of this lecture is that Dirac came in late 1920s, and he saw that the Schrodinger and the Gell-Mann was doing the same thing, and he thought that, okay, I can do something really interesting to actually simplify these things. And in later my videos, where I will solve this harmonic oscillator problem, like v of x will be half x squared, where I will show you that I am not going to do integral, I am not going to write any matrix, I am doing this algebra. You see here, this matrix arrived because of this simple algebra, like I have written here that what is the definition of psi I. So he thought that Dirac, one of the greatest genius, he thought that, okay, I can solve it in a very algebra form without doing any calculus or without doing any matrix algebra. I can solve with algebra, okay, with simple algebra. That's why he introduced these notations of cats and bras and all the expectation value and how the operator is acting on these cats and so on. So please let me know how you rate this video, and how do you like this video, and how do you like my teaching style, because my way of teaching quantum mechanics is completely unconventional. While I was learning quantum mechanics, I had a bit of problem of understanding that how these notations and how this why people say that this is kind of a matrix thing, this is kind of a kind of calculus thing. Calculus was familiar because 11 12 we do calculus so many things, but why this kind of matrices thing? I don't understand, I don't get it. And the computation and all the algebra which introduced Dirac was out of the course, it was bouncing over my head, that what's going on. So that's why I'm seeing that these cats and bras, why we are writing this representation of column matrix and row matrix. Okay, this is called the states. And what is the meaning of Hilbert? People say that Hilbert is infinite dimension. Now you see why, how this infinite dimensional things actually experience, because if this is goes for infinity, now this matrix also goes for infinity. Okay, now in computer you don't see any infinity, you see this largest number. So this largest number we say in an degree that okay fine, this corresponds to any kind of infinity, because infinity, computer doesn't know how to solve this infinity. Infinity is infinity. Infinity never exists in physical realm. Okay, it's our ignorance while we are doing this theoretically. So in computer you have to must set this exceeding limit of what should be the maximum thing you want to go for, and how precisely you are thinking. And what is the point of I choosing I choosing or h choosing so much smallest? Because whenever you get the function, like for an example, I haven't told you, like suppose psi for one dimensional, it will become this one. If I is my 1, so this smoothness will not be there. For I is equal to 4, this function like this one and this one. But for I is equal to 100, this is completely this one. Therefore, we have to take the step function h so much small that we will get a precise result. And to find this kind of small values, you need computer, because computer can do this kind of job. You cannot do this. So for this amusement of showing that how quantum mechanics is a matrix formulation, I have shown you how you can think about it. There are so many methods to solve quantum mechanics matrix numerically in computer. You can learn from different books, and that's what I so far going. And due to this matrix method, I have told you now that why this is not actually we see generally in quantum mechanics that EB is the ordering of operator is important, because in quantum mechanics you see, suppose you have two matrices, you apply this one, and now you write suppose x y is not always equal to y is equal to x in a very circumstances. So in quantum mechanics, that's why we are saying they are anti-commutate, means that they are not commuting the order, they are not independent of order. So these things actually comes from this matrix formulation, that matrix doesn't commute while multiplication. That's why these kind of notations, like these kind of operators will not compute. In quantum mechanics, remember that each and every operator can be written as in the form of matrix. So whatever the matrix follows, and matrix must belongs to Hilbert space, is the rule goes for any operator. Okay, there are very set of operators which follows this commutation relation, that a b is equal to b a, and that's why they share the same eigenstates as we have described in previous lecture. So I think it's enough for today, and we will meet in next video. Thank you very much, and please share and subscribe.